Okay, hello everyone. Myself is Tamilselvan from Erode Sengunthar Engineering College, Perundurai, Erode, Tamil Nadu. And now I'm going to share some topics about Boolean algebra and logic gates in the subject of digital electronics. So, uh, it is an essential subject for for designing any logic circuit in our motherboard and calculator and computer and robots, etc. So in this video, my first topic is digital system. So normally a digital system is designed to store and process and communicate the information in terms of digital form. So there are a wide range of applications like process control and communication systems and digital instruments, then consumer product, etc. So in the most common example for digital system is our computer. So it is a best example for digital system, right? So there are first of all the signals can be classified into two types. First one is analog signal and second one is a digital signal. Okay, so analog signal in terms of waves and digital signal in terms of numbers, that is binary numbers. So in the digital electronic subject, the most important thing is number system, because number system is only used to represent the numbers, because all the digital signals has been converted into has been transformed into numbers, so that it can be said as digital, right? So there are infinite ways to represent a number, that is binary number system, octal number system, decimal number system, and hexadecimal number system. In a binary number system, uh, and the base value is 2, because it contains only zeros and ones, right? So in octal number system, the base value is 8, because it contains 0 to 7 numbers, right? So in a decimal number system is most commonly used number system by human, because it contains 0 to 9 values. So the base value for the decimal number system is 10. In a hexadecimal number system contains 16 bits, so that the base value is defined as 16, right? So in our programming language and in our all the programming language, we have been used to identify a colors, or else we have been used to identify the 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 variety of colors in terms of hexadecimal number system. Okay, so next I can move to the binary number system, and the first number system is binary number system, and the binary number system is a most basic number system with the base value of 2, uh, that is zeros and ones. Okay, so this is the best example for the binary number system, the 1010.011 to the base 2. So the binary number system contains the base value 2, because it is based on only 2 digit, that is zeros and ones, right? Okay, so next I can move to the octal number system. In an octal number system, and the base value is 8 because it contains 0 to 7 values. So the most of the digits are in between 0s and 7. So the maximum number of inputs is 7 because 0 to 7. So totally 8 values. So the base value of 8 is defined by the octal number. So it is an example for octal values 175.36. There are this digit contains 0 to 7 values, right? So we can't define the octal number as 179.86, so because it can contain only 0 to 7 values, right? So number 8 is also avoided by the octal number because of the base value, right? So next number system is decimal number system. It is a most commonly used number system among the people. So so the decimal number system contains the base value 10. So that is 0 to 9 values. So it can contain integers as well as floating point, and it can be used to represent both the values. So it is an example for the decimal number system. So note that which is most commonly used by the people. Okay. So next I can move to the hexadecimal number system. In a hexadecimal number system contains 0 to 15 values. That is the total number of digits are 16. So the base value 16 can be notified by the hexadecimal number system. So in this hexadecimal number system basically used as an intermediate number system in a computer. So it is mainly used to represent the memory address as well as mainly used to represent the color values. That is double F hash double F 0000 is notified by the red color by default. It is one of the example. So the hexadecimal number system consists of 16 digit, that is 0 to 9 and A to F. So A means 10, B means 11, C means 12, D means 13, E means 14, F means 15. So it can contain 0 to 50 numbers. So there is a numbers up to 0 to 9. So there is an alphabets up to 10 to 15, right? So it is a best example for the hexadecimal number system. So the next I can move to the diagrammatical representation of the hexadecimal number system, right? So 0 to 9 can be notified in numbers, and the 10 is like as A, 11 is defined by B, and 12 is C, 13 D, 14 E, and 15 F. This is a hexadecimal number for the decimal numbers. So next I can move to the number conversion concept. So number conversion is basically done by the use of conversion methodologies. So basically the computer system accept the data in the decimal form, whereas all the data is stored and processed in the binary form in our computer. So the computer knows only zeros and ones, and our human knows 0 to 9 numbers. So we have to convert the decimal number into binary number for computer representation, and binary number into decimal number for human identification. So there is an intermediator like number conversion is used to identify the numbers by human and computer. So basically there are variety of number systems available. So first one is a decimal number system to other number system. That is decimal to binary number system, a decimal to octal number system, decimal to hexadecimal number system, and another form of number conversion is a other number system to decimal number system. That is binary to decimal number system, then octal to decimal number system, then hexadecimal to decimal number system. So this is an basic conversion between the numbers. So the other than this, there are lot of number systems, lot of number conversions available. It is first one is a binary to octal numbers, and binary to hexadecimal, then octal to binary, then octal to hexadecimal, then hexadecimal to binary, then hexadecimal to octal. Right. So so all these conversions except octal to hexadecimal and hexadecimal to octal, except these two, the above conversions is called as direct methodology. Okay. So except these two. So octal to hexadecimal and hexadecimal to octal conversion is called the indirect methodology. Why? Because we can't directly convert it into octal to hexadecimal and as well as hexadecimal to octal. There is no direct conversion here. So for what kind of methodology is used to convert this conversion? So first this octal, octal to hexadecimal. First we can take this octal to hexadecimal. So first this octal value has been converted into binary value, and that binary value has been converted into hexadecimal value. So there is an intermediate connection between octal to hexadecimal conversion is a binary value. So again I will repeat. So first this octal value has been converted into binary value, then that binary value has been converted into hexadecimal value, so that it is called indirect methodology, because there is no direct methodology to convert this octal value into hexadecimal value, right? And the same methodology has to be followed in this conversion also, hexadecimal to octal conversion. First the hexadecimal value is converted into binary value. That binary value has been converted into octal value, so that it is also called as indirect methodology. Okay. So next next I can move to number system conversion examples. So first one is a decimal to other number system. So decimal to other number system is called as LCM method. It is most remembered by LCM method, right? So decimal to other number system called LCM method. So please note on this. So there are three categories under this conversion. First one is decimal to binary. Second one is decimal to octal. Third one is decimal to hexadecimal. So in these three conversions, and the first conversion is decimal to binary. So the I have already told you that this conversion is also called as LCM method. So we have to convert the given decimal number into binary number. So the base value of the binary number is 2. So we have to convert this decimal number into binary number by the use of LCM by 2, right? So LCM by 2. So what is meant by LCM? LCM means there is a, for example, please take this example. So so the given decimal number is 147. So this is this number is divided by 2. 7 2s are 14 and 3 2s are 6. Remainder will be 1. Okay. So this 73 can again be divided into by 2, that is 3 2s are 6, remainder 1, then 13, 6 2s are 12, the remainder is 1. And the same methodology has to be followed until the number arrives 1. So after this number arrives 1, uh, we have to look into this down to upward for the solution. This 1 0 0 1 0 0 1 1 is a final solution to the base value. 2 is a exact binary value for the equivalent decimal value 147. 147 to the base 2, right? So please note down that we have to take down we have to take bottom to up value for the binary numbers. Okay, so bottom to up value, this is 1 0 0 1 0 0 1 1 is a final solution. Okay, so next I can move to the example number 2 in the same conversion with floating point numbers, right? So 62.8125 to the base 10, convert this decimal number into binary equivalent. So we have to convert this decimal number into binary value with, by the use of LCM by 2, right? And the same methodology and the normal division can be done in this example, in this conversion also, right? So 62, there are 31 2s are 62, there is no remainder, so we can put 0. Okay, then 31 here, then 31 by 2, 15 15 2s are 30, and remainder 1, and the same methodology has to be followed until the last value, right? So next, the final solution, I have already told you that. So please take this binary value from bottom to up level, right? So 1 1 1 1 1 0. So 1 1 1 1 1 0 is a exact binary value for this decimal number 62, right? So next we can move to the floating point conversion. So basically the floating point conversion, I mean the in the decimal to binary conversion, if the floating point values arrives, there is a small difference between the between the whole value and the floating point value. Okay, so there is a multiplication operation can be done when the floating point numbers arrives, right? So 0.8125 into 2, which is equal to 1.6250. So this one is a binary number. So next we can take this 0.6250 to the next step. So that value can be multiplied and we can get the final result as 1.2500. Okay, so the same methodology has to be followed until the zero arrives, or else we can stop by 2 or 3 steps. If the zero does not arrive, we can stop this conversion within 3 or 4th step maximum. Okay, so in this floating point example, I can take the final output as output from uh, top to bottom, right? So this binary numbers as a final result means we can take bottom to top for the whole numbers. For the floating point numbers, I can take top to bottom as a final output, right? So this 0.8125 equivalent binary value is 1101, that is 0.1101. So I can combine these two, so I can get the final result, right? So 111110.1101 is our final result. Okay, so is that clear? So next I can move to the another number system, another number conversion, that is decimal to octal value. So we have already known that the base value for the octal value is 8. So while converting this decimal value into octal value, I have to use the LCM method by 8, right? Because the base value for the octal number is 8. So I can use the LCM by 8 in this conversion, right? So example number 1, first I can take this example 1792 to the base value 10 to its octal equivalent, right? So this 1792 can be divided by 8 and we can get 224 with the remainder 0. This 224 has been divided by 8, we can get the remainder as 0. So this 28 can be divided into divided by 8, we can get the 3 8s are 24, remainder is 4. So the same methodology has to be followed while taking the final result in the LCM method, right? So 3400 is a exact octal value for the decimal value 1792 to the base 10, right? So next I can move to the example number 2 in decimal to octal conversion with floating point numbers. So this is an example with the floating point numbers. So this first I can take this 154 whole number by with LCM by 8, right? So 154 by 8 is 19 to the remainder 2, and 19 by 8 2 8 are 16, remainder 3. So 232 is a result of octal value for the decimal number 154. So next I can take this floating point number. So this floating point numbers arrives, there is a multiplication operation comes under this, right? So 0 sorry 0.789 into 8 it is equal to 6.312. So I can take this dot 312. So dot 312 into 8 is equal to 2.496. So I can move to third step, I can move to fourth step. So I can stop here up to fourth step. So I have already told you that if 0 does not arise, we can stop this multiplication operation by 3 step or fourth step itself, right? So I can take the final value 6237 from that it means top to bottom in the floating for the floating point numbers. Okay, so the final result will be 232.6237 to the base 8 is a final result, is a final octal number for the decimal number. So next I can move to the another number conversion, decimal to hexadecimal. So basically I have already told you that the base value of the hexadecimal number is 16. So I can take the LCM by 16 while converting the decimal to hexadecimal number. So we can directly go to example, that is 754 to the base 10 to its hexadecimal equivalent. So we have to convert the hexadecimal value. So the base value for the hexadecimal number is 16. So I can take the LCM method by 16. So the 754 by 16 is 47, remainder is 2. And this 47 can be divided by 16, and the 2 16s are 32, and the remainder is 15. Okay, so this 15 can be notified by F, that is a hexadecimal number. Okay, so so I can take the final result as it is done by the above conversions. So 2f2, right? So this 15 is a last and this 15, the equivalent number for this 15 is capital F. So 2f2 is a final output. So next I can move to the another one example with the floating point number while converting decimal into hexadecimal value. So so the example is 28.28125. So first I would like to take this 28 as a whole number by LCM by 16. So LCM by 16, so 116 or 16, so remainder is 12. This 12 is a decimal number, so its equivalent to the hexadecimal number is C. So 1C is a final output for the whole number 28. Okay, so 1C to the base 16. So next I can take this floating point value while converting this decimal number into hexadecimal number. So this 0.28125 into 16, that is 4.50000, right? So next I can take this 0.50000 into 16, which is equal to 8.40. So this in this step also the zero arise, that is all zeros arise. So I can stop with this step. So the final answer will be 1C dot 48 to the base 16 is a equivalent hexadecimal value for the decimal value 28.28125 to the base 10. Right? So these are all the some basic conversions. That is the first conversion methodologies, because the decimal to other number system, that is the decimal to binary number system, decimal to octal number system, and decimal to hexadecimal number system. Okay, so next I can move to another number system, that is other number system to decimal number, that is binary to decimal number, then octal to decimal number, then hexadecimal to decimal number. So these conversion is called as L methodologies. Okay, so the decimal number to other number system is it's also called as LCM method. The other number system to decimal number is called as L method, right? So there are three conversions under this category, that is binary to decimal number, octal to decimal number, hexadecimal to decimal number. So please note down that there is very important that, so please remember the base value of each number system, that is base value of binary is 2 and base value of octal is 8, base value of hexadecimal is 16, then base value of decimal is 10. So please note down. So it is a very important one while converting the number conversions, right? So in this other number system to decimal number system, first we have to see the binary to decimal number system. So in this binary to decimal number system, the input is binary and the output is decimal value, right? So it is also called as L method. So I have to use the L method with this formulas. So because first I can separate this binary number into examples. That is 0 into 2 power 0. This is the place which is 2 power 0. This is 2 power 1. This is 2 power 2. This is 2 power 3, and this is 2 power 4. Right. So in a basic mathematics, the 2 power 0, which is equal to 1. Right. So in this basic multiplication, 0 into 2 power 0, this 1 into 2 power 1, this 1 into 2 power 2, this 1 into 2 power 3, this 1 into 2 power 4, right? So so the after completing the multiplication, After completing the basic multiplication, I can get the final value and the final result as 30. That is 30 is a exact decimal value for the binary numbers 111110 to the base 2. Right. So next I can move to the same conversion with floating point numbers. That is 10101 dot triple one. Right. So we can separate this floating point number with the original number. Right. So as I already told you that this number is 2 power 0, this number is 2 power 1, this number is 2 power 2 in terms, which means I can take the right to left order. Right. So the and the different methodologies has to be followed while taking the floating point number. So it is a left to right order has to be maintained in floating point numbers, and only for floating point numbers. That is, this number is 2 power minus 1, this number is 2 power minus 2, this number is 2 power minus 3. That is, so 2 power minus 3 means 1 by 2 power 3. That is 1 by 8. Okay, so you can use any calculator for this operation, for this better operation, for this, and also for this accuracy concept, right? So the final result will be 21.875 to the base 10, right? So next I can move to the other number system. Other number conversion, that is octal to decimal value. Okay. So octal to decimal value. So we have already known that the base number for octal number is 8. Okay. So I can take this octal to binary number conversion by L method with the multiplication of 8. Okay. So consider this example number 1. So in this example, there is an octal number is 540. So the first digit is 8 power 0, and second digit is 8 power 1, and the third digit is 8 power 2. Right. So 0 into 8 power 0. So anything power 0 which is equal to 1 based on a basic mathematical. Right. So basic mathematics. So 0 into 8 power 0, 4 into 8 power 1, and 5 into 8 power 2. That's all. So these basic mathematics has been prepared by the use of number conversion. Okay. So next I can move to the same number conversion with floating point numbers. So this floating point numbers, the same methodology will be followed through in octal number system. And the same methodology what we have followed in binary number system, and the same methodology has to be followed in octal number system also. But the binary number system base value is 2, so I can multiply the 2 power 0, 2 power 1, 2 power minus 1, 2 power minus 2, etc. So this is an octal number system. So there is a base value 8 is octal number system. So I can multiply, or I can divide whatever it may be the operation. I can take the 8 to the power, right? So the consider this example, this 24.36. So this 4 into 8 power 0, and 2 into 8 power 1, 3 into 8 power minus 1, 6 into 8 power minus 2. So better use the calculator for the accuracy output, right? So the final output will be 20.465, right? Sorry, 465, not 465, right? So the next I can move to the hexadecimal number system, right? So hexadecimal number system. So the base value of hexadecimal number is 16. So the same methodology has to be followed in hexadecimal number system as like octal number system and a binary number system. So the same concept, so the same scenario has been followed in this conversion also. So there is a conversion between hexadecimal to decimal number system. So because of this hexadecimal value based 16, so I can take the 16 exponent value, right? So 16 exponent value. So this 28d to the base value 16 and d into 16 power 0, there is the 13 is a equivalent value for d. So 13 into 1 is equal to 13, and 8 into 16 power 1 and 2 into 16 power 2. So 653 is a equivalent decimal value, right? So the 653 is a equivalent decimal value for this hexadecimal number 28t to the base 16, right? So next I can move to the example number 2 with the floating point values uh, by the same conversion, that is hexadecimal to decimal conversion. So hexadecimal to decimal and the same methodology has to be followed in the floating point also. That is, so after floating point value, so there is a multiplication in terms of negative value, that is 16 power minus 1, 16 power minus 2, 16 power minus 3. So before floating point, there is a positive value with the exponential part, that is 16 power 0, 16 power 1, 16 power 2. And please note that, so the before floating point we can choose the numbers from right to left. After floating point we can choose the numbers from left to right. That is, so this is another one example. So 8 into 16 power minus 3 and 1 into 16 power minus 2 and 4 into 16 power minus 1, that is b into 16 power 0. B stands for 11. So 11 into 16 power 0 means 1. Okay, so the same methodology has to be followed for to all the inputs, right? So finally I can get 1723.25585 is a decimal equivalent number for the hexadecimal number 6BB.418, right? So these are all the basic conversions available in number conversion. Okay, so other than the basic conversion, and our next conversion is uh, other conversions to the BCD method. Okay, so there are 6 types of conversions available under this BCD method. So please note down the BCD values. That is, this is a very important inputs. So if you don't remember the inputs, we can't do any operation. Okay, so please note that, and please remember that this table value, that is BCD values. Okay, so there is a octal code, means there is a total of 8 numbers, that is 0 to 7. There is a hexadecimal code, is there is a total of 16 numbers, that is 0 to 15, right? So next I can move to the other conversions. Other conversions means first one is binary to octal value. So binary to octal value has been converted in direct methodologies. That is, each group given binary digit into 3 digit. That is, um, there is a binary number as a input. I can separate the 3 digit because in this binary number has been converted into octal number. That octal number is contained only 3 digit, so I can separate 3 digit from the right end in this binary number. Okay, so take this example number 1. So 111000101. So I can separate from the right end. So 101 I can separate here, 001 I can separate here, 1 1, there is no value here, so I can add the 0 to the left, right? So this 0 1 1 is equivalent octal value is 3, and 1 0 0 equivalent octal value is 4, 101 for the octal value is 5. So 345 is a final octal number for this binary number 111000101. Is it clear? So again I will repeat. So I have to separate 3 digit from the right end. So please note it down. From the right end, I have to separate 3 digit in the binary number, right? So next I can move to binary to octal number. Example number 2 with the floating point number. So the same methodology has to be followed from the above example, right? So this consider this dot value. After this dot value, 0001 is there. So I can separate the 3 digit from the left end after dot value, right? So 000 has been separated, and only a single digit is there. So I can add 00 from the right end. Okay, so 100 it is there. So before the dot value, so the same methodology has to be followed as it is from the example number 1. So in this example, so 00, this I mean the numbers has been separated by 3 digit from the right end, right? So 001 has been separated, 101 is separated, 111 is separated, and the final one occur, that is in the binary number, right? So this 111 is a decimal number, and the 101 is 5, 100 is 4, 000 is 0, 100 is 4. Okay, so the 754.04 is a final octal value for the given binary number, this 1111011100, right? So consider this uh, this table for all the examples. Then only you can easily identify the decimal number for the octal code, for the 3 digit octal binary code, right? Okay, then our next conversion is binary to hexadecimal. So binary to hexadecimal means there is a 4 inputs available in the hexadecimal value, that is 0 to 15. So total number of inputs is 16. So that the 16 is a base value for the hexadecimal numbers. Okay, so each and every input consists of 4 digit in the hexadecimal value, right? So first we can take this example, that is 111000101. So as it is, I can take the 3 digit number from the right end in the octal conversion. This is an hexadecimal number conversion. So each and every input consists of 4 bits. So I can separate 4 bits from the right end in this concept, right? So 1010 has been separated, 0111 has been separated, that is 1110 has been notified by E, and 0101 has been notified by B. Then E5 to the base 16 is a exact hexadecimal value for that binary number, right? So please note it down this table in every example, so that we can easily put the value without any hesitation or without any unwanted late, right? So next I can move to the example number 2 in the same concept with the floating point numbers, right? So the same methodology has to be followed as binary to octal value. So octal value means there is 3 digit, in the hexadecimal value means there is a 4 digit, right? So so after this floating point values, there is a separation from the left end, right? So separate this binary number from the left end after this floating point, right? So before this floating point, and the same separation with 4 bits from the right end, right? So consider this example number 2. So consider this number after floating point, so 110101, right? So 110101. So 1101 has been separated. Remaining 01 is there. So we can easily add it by zeros, right? So 0100. I can easily add it. So next I can move to the whole value. So whole value means I can take this 4 digit separation from the right end, right? So from the right end means 1011 is separated, 1001 is separated. So last and final is one and this, I mean a single input is only there. So I can add it. I can add 000 in this example, because so each and every separation and each and every bit consists of, I mean each and every section consists of 4 bits, right? Because this is an hexadecimal number, right? So and the another conversion is octal to binary. So octal to binary value is very easy to convert when we compare to another conversion. We can directly move to the binary value in a single step. That is, so in this example, the most and foremost thing is this table, right? So convert this octal number 6347 to the equivalent to binary equivalent. Okay, so this 6 is I mean decimal number, I mean the octal number. So the octal number in terms of binary is 3 bits. So I can easily identify the 3-bit binary value for that octal number, right? So 6, so octal number 6 is 110. Octal number 3 for, I mean the binary number 011 is equivalent to the octal number 3, and this octal number 4 is 100, and octal number 7 is 111. So because there are only 3 bits are available. Okay, so 3 bits are available because this is an octal number. In the same methodology in hexadecimal number means we can easily identify by 4 bits, right? So next I can move to the another one example with the floating point number. That is octal to binary with the floating point number, and the same methodology has to be followed with the floating point number also, right? So 3 is 011, 7 is 111, 5 is 101 dot, 1 is 001, 6 is 110. So I can combine these binary numbers as a in the final output. Okay, so next conversion is hexadecimal to binary. So I have already told you that there is a 4-bit value in terms of binary numbers for hexadecimal number. Okay, so we can directly go to example for better and easy understanding. So first I can choose the 5C8. Okay, so 5C8 to the base 16 is the first example. So I can easily derive the equal to hexadecimal value with 4-bit binary number. That is 4-bit binary number means 4-bit binary number for the hexadecimal number 5 is 0101. For the hexadecimal number C is 1100, and for the hexadecimal number 8 is 1000. So I can combine with the final result, thus 0101 110 1100 1000 as like, right? So next I can move to example number 2 in the same conversion with the floating point, right? So consider this example 43.10 AB to the base 16 to convert it into binary equivalent, right? So so the hexadecimal value for the the binary value for the hexadecimal number which contains 4 bits. Okay, so 4-bit means I can take this 4 means 0100, 3 means 0011. So here it is the hexadecimal equivalent number, right? So 1 is 0001, 0 is 4 zeros, capital A is 1010, capital B is 1011, right? So this is an equivalent binary number for the hexadecimal number 43.10, capital A and capital B, right? And the last and final number system is octal to hexadecimal. So octal to hexadecimal means there is an indirect methodology, because this octal value has been converted into binary value first, and that hexadecimal that binary value has been converted into hexadecimal value. So there is no indirect methodologies available while converting the octal value into hexadecimal value. Okay, so that's why it is called indirect methodology. So there is no straight conversion. So first we have to calculate we have to convert this octal number into binary number. So that binary number has been converted into hexadecimal number, right? So first I can take the example as 2327. So there is first this 2327 octal value has been converted into binary number first. So this is an octal value conversion. So I can take the 3-digit binary numbers for each number. That is 2 is 010, and 3 is 011, 2 is 010, and 7 is 111. Okay, so that binary number uh, so the equivalent binary number for the octal value 2327 is 010011010111 is a equivalent binary number. Okay, so that binary number has been converted into hexadecimal number. So we have already seen this concept as, so I had to separate 4 bits to convert an hexadecimal number. So consider this example, and also continuation of this example. So I can take 1110, I can separate this. 1011, I can separate this. 0010, I can separate this. Okay, so 4D7 is the equivalent hexadecimal value for the binary value. Okay, so next we can move to another example. So another example for octal to hexadecimal number is 463.52. So 463.52 is an example number 2. So first I have to convert this 463.52 into binary with 3 digit. Okay, so next I will have to convert by the continuation of above logic. So next I have to convert this binary number into hexadecimal number. So there is a separation between there is separation of 4 bits. Okay, so 4 bits means so after this floating point I can take the 4 bits after uh, floating point value, right? So 1010 separate this 10 only available, so I can put 00 instead of giving the complete binary values, right? So in the whole number, and the same methodology has to be followed from the right to left hand, right? So right to left hand. So this is an octal to hexadecimal conversion. Okay, so I have already told you that this octal to hexadecimal and hexadecimal to octal are the indirect methodologies, because there are no direct methodologies. There is no direct methodology while converting the octal to hexadecimal as well as hexadecimal to octal value, right? So it means I will have to convert the above inputs. Okay, so to take this number, so in the whole number 1100 has been separated, 1100 has been separated, so this only there is a single bit only available, so I can add 3 zeros before the single bit, right? So this is the we can easily identify it by the use of this table. So 0001 is equivalent to hexadecimal number is 1, and 0011 is 3. This is also 3. 1010 1010 is A, that is 10. Then 1000 1000 is 8. So I can combine. I can easily combine with this hexadecimal equivalent. Okay, so there is an another indirect methodology is hexadecimal to octal number. So in this concept, first we have to convert the hexadecimal number into binary number. That binary number has been converted into octal number finally, right? So first we have to convert the given hexadecimal number into binary number. Okay, so we can directly go to the examples. So take this example: A to DE to the base 16, right? So capital A is A. So the 4-bit binary number for capital A is 1010, and 2 is 0010, and capital D is 1101, and capital E is 1110. Okay, so and the step 2. So that is a final step. This is why, because this hexadecimal to octal value is also called as indirect methodology, because there is no direct methodology available while converting the hexadecimal to octal value, right? So consider this example. So I can get the binary number after completing the first step. So next I want to move to step 2. So in the step 2 concept, I can take these binary numbers as a input, right? So there is a whole number, so there is no issues while converting this binary number, right? So I can separate this 4 digit in this input, because so 0111, then 1001. So in our logic, there is a final conversion is octal number, so I can choose only 3 digit in the binary number. Okay, so 011 and 110, so on, so, right? So 001 is 1, 010 is 2, 001 011 011 116 110. Okay, so this is an equivalent octal value for the hexadecimal number by the use of binary numbers. Okay, so next I can move to the another one example for the hexadecimal to octal conversion. Okay, so first we have to convert this hexadecimal value into binary value. That binary value has been converted into octal value as it is our previous logic. So consider this example number 2, AC 5.4D. Okay, so first we have to convert this hexadecimal value into binary value, into 4-bit binary value. Okay, so capital A is 1010, capital C is 1100, then 5 is 0101, then dot 4 is 0100, then capital D is 1101. Okay, so finally I can get the binary value. So that binary value has easily converted into octal value by the use of 3 digit separation. Okay, so 3 digit separation. So in this example number 2, so there is a separation after the floating point is very easier. Okay, so in this final binary value, I can separate this number into 3 digit, because it is an octal value conversion, right? So 010011010, that is a 232. Okay, so this so before this floating point number, so 101 000 110 101. Okay, so this 101 has been the uh, equivalent decimal value, and also equivalent octal value also. Okay, so in the next class I can move to the binary addition. Okay, so thank you very much for watching this video.